That's an actuary provider.
Or try. It's just random that you succeeded. Autumn regress by 1 day on Tuesday. Oh, that's good. Characteristic equation. They are used to determine whether the roots lie outside or inside the unit circle, but it all starts with, phi of b. We have seen phi of b, theta of b. The book uses pi of b. I personally find it unnecessary, but I will mention it later, because when we switched from one side to the other side, we just kept it as, 1 over phi or 1 over theta, but raised -1. But the pi part is no different from what we did. Instead of calling it as the reciprocal function, they call it as pi of b. I looked at it this morning. There isn't something special about pi of b, but I will mention it later when we get to it soon. So phi of b is going to be a polynomial in b, which is the backwards operator, and we are going to use phi of b to determine whether the series is going to be stationary or not. There are other conditions. One is causality, the other is reversibility. We will address that also.
Aaron just messaged me to center the video onto the whiteboard.
Ah,
Let's see if you have a response for that.
phi of b is the polynomial in b, and we are going to use it to determine whether the roots lie outside the unit circle, inside the unit circle, on the unit circle. We can write an expression that is in terms of b, book uses m. And what was the condition last time? What is m? That's all I know. 1 over b. That works out nicely because we are going to set it equal to 0, so the denominator part is going to go away. What do I mean by that? If I took an AR2 model, let's see, let's make something up. 1 minus 0.25 b plus 0.12 b squared, AR2 characteristic equation. We are going to set that equal to 0 to find the roots. Well, if I convert it to some polynomial as a function of m, using m equals 1 over b, b would be equal to 1 over m. We multiply by m squared on both sides, and end up getting m squared minus 0.25 m plus 0.12, entire thing divided by m squared. Yes? But I'm setting it equal to 0, so that denominator is going to vanish. So we simply have m squared minus 0.25 m plus 0.12 equals So mathematically speaking, or algebraically speaking, it's not doing anything wrong. Okay. Now that we have the characteristic equations, we can determine if the roots lie outside or inside the unit circle. A bit of complex analysis. Let's just throw that in here. Did we take complex analysis? How many of you know complex numbers? No. Never heard of it?
But we know complex numbers are going to have complex analysis.
Okay. They're very simple human beings, actually. We are complex. Let it go this semester for some reason. They might actually invite me at the end of the semester. Lily's got the experience. Okay. So a quick introduction on a complex number. Pretty much every number that we encounter in life is a complex number. We just don't see it that way. The standard form of a complex number is a plus I, b. Oftentimes, people denote a complex number using the letter Z. So we'll stick with that. The real part of Z is RE of Z. And IM of Z is the imaginary part. Of Z. What is the imaginary part? Do we know what an imaginary number is? Or when it happens? When do we get that imaginary? Negative square root of -1, right, or even root. So the I part is simply square root of -1. Something showed up on my Quora feed, and someone asked, well, what is the point of having imaginary numbers? The number is imaginary. And someone responded to this entire paragraph and said, well, if you can't understand what an imaginary number is, you lack imagination in understanding what math is. It was funny. I thought so. We don't call it an imaginary number because we lack imagination. Square root of -1 is something that we cannot express directly in math. Sure, I can put square root of -1 anywhere I want, but it is best to write it in simpler terms. People take I for imaginary. There are textbooks that actually use J instead of I. Perfectly fine. Good. So I is the most commonly used notation for imaginary number. Okay. Complex conjugate. The conjugate of Z, I'll just put Z, so C simply A minus IB. You might wonder, well, what is complex analysis doing in time series? Well, we are going to deal with roots of a polynomial. What do we know about roots of a polynomial? First order polynomial or first degree polynomial is going to be real, right? Quadratic could be real, imaginary, cubic, same, quartic, same, and beyond a certain point, after degree 5, you are going to have complex roots, right? So we need to know what they are. And if we have complex roots, for example, a third degree polynomial, one of the roots, if I tell you is complex, what can you say about the other roots? All three of them? Or all two of them?
There'll be at least one.
At least one, so you are agreeing that there has to be 3 complex roots. Andres, did you have to say something?
Yeah, I was gonna say they come in pairs.
They come in pairs, right? So if one of them is complex, there is going to be one more complex root, that's it. The other one will be real, right? Same, if you go to higher order polynomials. Since we have a characteristic equation, in this case, that is quadratic. If I go to an AR3 model, it would be cubic. If I went for an AR4 model, quartic, AR5, pentic, yes. We typically don't need anything past 8. It's very rare. But from the theoretical standpoint, we can keep on going. Correct. Okay. So, few things that we've got to know about a complex number. The absolute value is set, but it's not absolute value, rather the magnitude of z. What is the magnitude? The magnitude is simply square root of a squared plus b squared. Don't know what Q is, but I'm going to use theta. Phi is also a notation for this, but we already used phase, so we'll have theta. It is tangent inverse of B over A. In this case, inverse literally means inverse. Unlike, the inverse, not the inverse is, unlike the times when we wrote psi raised -1 of B, that's not an inverse function. It's 1 over psi of B. Okay, but here I literally mean the inverse function. That is called the phase. Shows up in Sigmund Christie all the time. Let's see if we can get this spectrum today. If not, it will definitely show up on Tuesday's letter. So we've got magnitude, we've got phase. Erase that one. Thanks. Another important formula that you encounter in complex analysis is the Euler's formula. Do we remember what that is? No. I mean, you don't remember it?
No, you can do it.
Understood that?
I was gonna say,
Put all these actuaries to shame.
there's like a lot of signs.
Sines and cosines, okay. The same complex number can be represented in that form, where you have the magnitude and you have theta, and theta comes from here, magnitude comes from there, so you can represent it in that form. You might wonder why. Any thoughts? I'll give you a hint. I'm going to distribute that magnitude and write it this way. Magnitude of z times cosine theta plus I magnitude of z sine theta. It's got to do with something that I drew here last time.
Yeah, I was about to say, I was like, I don't know.
I know what I did.
I don't know why you got a smaller number.
0.646. Bad math, I'll blame this on the test anyway. So that's what we have. 0.25 over 0.24, 1.04 plus or minus I, and that one 2.69. It's fine. It helps you keep your mind sharp. 1.04, plus or minus I 2.69 would be the roots. Now, we have a problem, sort of. Do you believe that there is a possibility of non-stationarity or no?
Well, I don't think it would be in the unit circle, so.
It's not going to be. You can't jump to a conclusion by looking at the real part and say, oh, it is 1, so it has to be on the unit circle. You've got to account for the imaginary part also. Easier way to recognize whether it is going to lie on the unit circle or not. It's simply find the radius. The radius of the circle that we are looking at, simply given by the magnitude of that complex number and square root of 1.04 squared plus 2.69 squared square root of 2.7 2.6 something. Got to be a bit bigger than that, because this is 2.7 squared.
It's the square root of 8.31.
8.31. Which is approximately 2.9.
Yeah.
One more decimal.
It was 80.
80. So 2.88. So it doesn't lie on the unit circle. It actually lies on a circle that has a radius of 2.88. So it is going to be stationary. I could have come to this conclusion at the very beginning. Ethan? How?
Could have just used the magnitude.
Without even doing any of this, I could have come to a solution. that it is more likely that the series or model is stationary.
The weights.
The weight over here, the weight's negative 0.25, 0.12. I wrote it in a way so that they would be absolutely similar, right? It's decaying slowly. So it makes sense, hopefully. If we found 1 over m, which is b, m would simply be equal to 1 over b. I will have 2 roots, m1, which is 1 over 1.04 close by 2.69. M2, 1 over 1.04 minus I, 2.69. False. No false. We can do Euler's formula. Or we can simply do the conjugate. Multiply and divide by the conjugate. If you multiply and divide by the conjugate, the numerator will be 1.04 minus I 2.69. The denominator will be the magnitude squared.
But so, what is that exactly?
So I should probably write this. I'll put it as a remark here. If you have 1 over a plus ib, did I forget that? No. You multiply and divide by the conjugate of a plus ib, which is a minus ib. So the numerator will become a minus ib. Denominator is a plus ib multiplied by a minus ib. You do FOIL, you will end up getting a squared plus b squared. Not a squared plus b squared, it's the magnitude squared. Read the same thing again. Magnitude squared. Okay. One point zero four minus I 2.69 divided by, we found the magnitude of that to be 2 point.
So the 1.04 minus I 2.6, that's the conjugate of M1. You're doing that for M1, not M2.
I'm doing it for M1. This entire part is M1. One point zero four minus 2.69 I. Denominator is the magnitude squared. So if you square, you will get 8.31. So I put 8.3 there. Split it up, you will have 1.04 divided by 8.31 minus I 2.69 divided by 8.31. Which is approximately equal to 0.116.
Point one two five.
That one? Exactly 0.12?
No, no.
Oh, okay. It's 0.12.
515. And then we keep going.
One over 8 is 0.125. We're dividing by a bigger number, which is 8.31.
Yeah, but it's still close enough.
Oh, here it has 0.12.
I mean, you can do it in your own calculator if you want.
2.69 divided by 8.31. Oh, it's dividing 1 over 8.31. It's actually 1.04 over 8.3. Is that in part?
0.32.
Okay. Do I have to repeat this process to find that second root? Not necessary, because the roots occur in pairs. So the other root is simply the conjugate of that. So 0.13 plus I 0.32. Good. I have the roots for the characteristic equation expressed in terms of m. The roots of m, do they lie outside the unit circle or inside the unit circle? Inside. You don't have to find the radius again. That's 0.13. You square it, you're going to get a small number. Square it, you're going to get a small number. Both terms are between 0 and 1, which would simply mean you square and take the square root. That result is going to be between 0 and 1. So the radius of the circle that you are looking at will be inside the unit circle. So that point is going to lie inside the unit circle. Okay? This is what I was referring to last time. If you are going about with an equation that has b, you want the roots to lie outside the unit circle. If you are solving for m, it has to lie inside the unit circle. Good. Erase. I can rewrite that expression in terms of m as m squared minus 0.25 m plus 0.12. You set that equal to 0. You solve for the roots. I will start here. The first root is m1, the second root is m2. Yes, no, maybe. That is. M is my variable in the equation. Whether you call it root, call it 0, same thing. It is where the characteristic equation is going to become 0, yes.
Why isn't 0.12 the coefficient for m squared?
Wait, what? I'm going to repeat that question.
Why isn't 0.12 the coefficient for m squared, which is the coefficient for b squared?
So I am dividing by b squared on both sides, right?
Oh,
So that's how I got from equation in terms of b to equation in terms of m. I wrote it this way because it's easier to understand what I'm about to do. So that I can rewrite as 1 over b minus the root times 1 over b minus the root equals 0. Not doing anything wrong, agree? Common denominator, multiply by b, doesn't matter which way you look at it. I'll have 1 minus 1b times 1 minus m2b equals 0. Agree? So thus far, all I did is I took the characteristic equation, factored it, wrote it that way. Good. So in general, instead of those numbers, different should have wrapped in that. In general, if I have an AR2 model specified this way, 1 minus V1B minus V2B squared, that is the characteristic equation of an AR2 model. Do we agree? I can write that this way. No matter what AR2 model I have, do you agree? So, going with what I have, 1 minus M1B times 1 minus M2B. Erase. Perhaps there is a reasoning behind this. Your book refers to that as G1B. And 1 minus G2B. Good. That's just notation. So this has nothing to do with that in terms of what we solved. This is just the book's notation. So I don't want you to get confused when you look at this expression and start wondering what G is, right? Same thing. Okay. maybe I'm just getting old. Every time I write ARP these days, it reminds me of AARP. If I extend this idea to an ARP model, what would uppercase V of B equal to? I'll give you a hint. AR1 model had a simple linear equation. AR2 model has a quadratic equation. AR3 is going to give a cubic equation for fourth degree polynomial, 5, fifth degree polynomial. Regardless of which case I'm looking at, I can rewrite V of B in a set form. What is that form? How many? Go ahead.
I would say it would be the product of one of P of 1 minus 9P.
Very good. So going with the book's notation, the book calls M1 as G, M2 as G2. So 1 minus G1B times 1 minus G2B. Dot, dot, dot. 1 minus GP. A polynomial can be expressed as a product of linear factors, right? Or quadratic factors, if there is multiplicity. So, good. I don't want to write that. So, uppercase I 1 minus GI times B. What does uppercase pi stand for? The product. Just like the summation sign, which sums individual terms, that is the product of all terms that you have in the sequence. You multiply all the thing, and that's what you will get. Good. Is this process going to be any different if you go for an MA model? Not really, it's not going to be. Reason being, if I know that I can move from AR to MA infinity, MA to AR infinity, so I'm just flipping back and forth. So this process holds true for whether it's AR, MA, or no, doesn't matter. Good. So the goal is accomplished. We took our characteristic equation, which is simply our AR model in this case, expressed it as a product of linear factors. You might wonder, why did he even bother? Why indeed? I will give you a hint. Those factors have something to do with what we have done multiple times with an AR1 model. Multiple times. I'll also give you another hint. It has something to do with that AR1 model and infinity. You impress me for an actual. Geometry theory. Every single time we try to convert something to AR infinity or NA infinity, we needed a geometric series. Agree? And the geometric series was easy if we were able to write something as 1 over 1 minus 0.18b. Right? That might have been my very first example this semester. I think so. Correct? I can write that using geometric series. Our goal is to take this, now that I have them as practice. Don't write this down, we can write this later, because it won't make any sense here. So if I have that, hypothetically, don't write this down, just pay attention. I want to somehow go from here to there. You know, so that I can use individual terms. Is there a way to go from here to breaking this apart and writing it as a bunch of songs? You will have to do your part. That's the hint. Partial fractions. Calculus 2. I can simply rewrite each of those this way. Right. Now I have that expression expressed in this manner. Well, this part right there can be expressed as a geometric series. That right there expressed as a geometric series. As long as I can solve for A1 and A2, I can represent it as an infinite series. Does that make sense? Yes, no, maybe. So the point I'm trying to make is these roots play a significant role in addition or alongside A1 and A2. So if we can find A1, A2, what are we going to use to find A1, A2? We are going to use the data that we have. If we can solve for A1, A2, and we know that those are related, then I can work backwards and find P1, P2. Agreed. I can estimate the model. So to understand this process, I started with a model where I knew Phi1, where I knew Phi2, and I showed you that that can be expressed as a product, and that can be expressed as this. If I have the data at hand, I can work backwards, starting here, and find Phi1 and Phi2, because that is our ultimate goal. Agreed? Given a series, we want to know Phi1, we want to know Phi2, if it is an A object model. Do we get the idea? Big picture? Okay, we'll stop there.